Okay, so I think it's after 1:20, so we got a nice small group. We're going to be working through very introductory stuff into Scikitlearn. Along with me presenting in front, John Schreck, who's here on the Zoom, but also here in 3D space. If you have a problem or 7 hands goes up at once, John will be helping me kind of come around the room and help you out if you have questions or comments or deep thoughts. Nick, are you good? Are you on? Okay, perfect. So before we get too far down the road, there is this notebook called Update Workshop Material. It is just one cell that has Git pull alert. If you can click on it and then do Shift Enter to run it, that's going to get you the latest and greatest notebooks, which we have. I fixed some spelling errors and other sorts of fun odds and ends. So that was good. So from there's Users Workshop, 3_Wednesday, breakout sessions, and then there should be Intro to Sklearn. As is the name of the notebook, I should say Introduction to Machine Learning at the top. If people are there, if you could flash me a thumbs up or something like that. Okay. Are you good, Z? Nick, how are you doing?
Yeah. 2 shakes of the lamb tail to get on there.
Okay, groovy. Okay, so this is introduction to Scikitlearn. For those of you not familiar with Scikitlearn, it is a great machine learning package written in Python. You can do clustering, regression, classification. Really, it does everything but deep learning. You can make a neural network in Scikitlearn. Even on their documentation, they're like, for education or toy use only, I would not recommend making a 7-layer fully connected deep neural network in Scikitlearn, even though you can do that. If you think about getting your start in anything in machine learning, this is where I would be. And also for most problems and most people, this is where you should end. While deep learning is cool, it can answer a lot of things, it's definitely not necessary for a lot of problems. If you use a lot of only station data or random observation data, you can kind of sit within the Scikit-learn ecosystem. If you want to work at a business and everything's an Excel sheet or tabular data, Scikit-learn is also where you want to be. That being said, if you want to go to image recognition, 3D volumes, or more advanced sort of modeling purposes, deep learning is definitely substantially better for those sorts of use cases. But okay, now let's dive into the notebook. For those of you not familiar with, here I'm going to get rid of the left. Okay. So for those of you not familiar with Python, we're going to import in a bunch of packages. And so, at the top, we got pandas, numpy, matplotlib, seaborn. I'm importing this Palmer penguins data set, so we're going to be doing a lot of prediction on different penguin species and penguin body types. I am not a penguin expert, but it is a nice data set to sort of work with. That's an alternative to Iris. Then we're going to import Scikit-learn, or here it's Sklearn. And then if you want to print the version out, should be 1.2.2 or something above 1 is all that we're looking for. To load in the data set itself, it's just going to be pandas data frame. And so with this, we have every column labeled. We have species, which island, bill length, bill depth, flipper length, body mass, sex, and then what year the data set was collected. So again, you could imagine your data sets also being, maybe having a collection of floats or numbers and then a collection of objects or classification or things or, car color, tornado versus cloud, versus sunny day, those sorts of classification tasks. So, I don't promise to be a biologist, but it's a nice, handy data set to use for this sorts of things. Just to go one step further from sort of my Monday talk, df.describe is a nice way to go, where you can sort of get those quick EDA stats where you can get a mean, percentile, standard deviation, min-max. And so this could be a quick way to figure out some quick stats from your data frame without having to write too many lines of code. This is a box plot done with Seaborn. Just so I'm going to unpack it from the inside out. So I'm defining that the data equals this data frame, and then I'm saying what columns I want to use. You could do a correlation matrix also with that same data frame. With this, I'm only using the floats, and you can kind of see, which input features might be correlated to one, or which one might not be super correlated to another. So this isn't a super exhaustive, data exploration. Before you do any machine learning, I would definitely plot your data. If you're not familiar with Anscombe's quartet, it is terrifying if all you do is look at stats. Is someone not? If I say Anscombe's quartet, does everyone know what that is or no? Okay, we are all going to be terrified together. So Anscombe's quartet is these 4 different plots, but they all have the same descriptive stats. Are these telling you different things? Maybe are these different relationships? Would you want to edit some of these data points? For sure. And so while they might have the same standard deviation and slope, how would you treat these? Out of these boxes, which one would you like the most? For me, I'm a upper left. If you're a bottom right, that's kind of chaotic. But, so it's like, plotting your data, even if you're a machine learning person, should never go out of style. The other sorts of thing is you're like, well, what about if I have 1 million data points? Subset it to 5,000, either randomly pulled, if that makes sense, or if it's time series data, pull a couple years throughout your data set and sort of look at it like that. And I totally get that this is, hard, but I can't tell you enough that plotting your data is so important. Okay, sorry, miniature soapbox. So from this, I also want to see how many number of unique species we have, and then we're also going to drop the year, because I don't really care when the data was collected. In this case, that might be key for you. We can also get a count of all the nands in the data set. For this, we're just going to drop them. For you, you might want to explore why they are nands, how to fill these in. You can maybe interpolate them, but this is just more sort of a data exploration step. Now that we have removed all rows with nands, we can do a new describe to make sure that our stats and metrics haven't changed a whole ton. Okay, now sort of a beginning EDA, super fast hot take on what to do. Is there any questions so far about plotting your data, how to do some basic sort of pandas, dropping, NAND, exploration, or any general questions? Okay, groovy. So the other thing we're going to do, we're going to pre-process this data set. So you're like, why do I need to process this data set? Most machine learning models like to be scaled. And what that means, you don't want one input feature or input vector to range from 0 to 5,000, then the other one to range from 0 to 0.2. Because if you think about, finding a local minima, it's going to be much easier on something that's scaled from 0 to 5,000 than from 0 to 2. And so you want to scale, normalize, make it into a normal distribution as possible. Now, that might not be what your data requires, or that might be too much data munging. And again, you would want to explore that in sort of the EDA part. So if your data looks like a big hump and then like a bunch of little sawtooths at the end, you might need to come up with a different way than just normal standardization. So we're going to make a copy of the data frame, check out the D types. So for this, anything with a number is a float. You can also have int. Objects are generally text. We're going to make a variable with the float columns. We're going to scale. We're going to use the Scikit-Learn pre-processing standard scaler. Oof, sorry about that. And then only fit on the columns that have numbers in it. So if you have a column with red, green, blue, how do you normalize or scale that? So that's why we only want columns with numbers in it. And then again, after you do we're going to make a new data frame called df scaled. And then after you see this, now you have negative bill length, which doesn't make sense physically, but makes sense from a data science perspective. Last thing we're going to do here, we're just going to resample the index to make sure that all these rows are all jumbled up. But for a time series data set, you probably wouldn't want to do that. So again, that's just specific to this Penguin data set. So if you see here on this df scaled that the mean is not quite 0, it's trying very hard. E to the minus 15, e to the minus 16. So it's centered at 0 with a standard deviation very close to 1. That's basically what we did with all those input numeric features. All right. Questions, thoughts? I know it's a post-lunch. It's hot out there. I was ready for a nap. But anyone have any questions so far?
When would you scale? When would you want to scale a data set, and when would you maybe not want to? Like, what would some situations be where you wouldn't want to do that, or you need to pick a different?
Yeah. So when would you scale versus not scale? I would say in general, scaling is good. I would say if your data is not anywhere near sort of a normal distribution, how you scale it might require some more thinking. This is just the standard scaler within Scikit-Learn. There's like 4 or 5 or 6 different scalars you can pick if you're like log normal, or there's all this sort of workflow depending on how your data looks. With decision trees and gradient boosted decision trees, those are a very specific type of machine learning model. You don't have to scale. Sometimes if you scale the inputs, you can get better performance or better interpretability, but it's not a definite need. If you're using neural networks, you're going to want to scale every time. Like, I can't think of a time where I'm using a neural network where like, oh, I'm not going to scale. So.
Is there an easy way to picture how that benefits the machine learning process?
A lot of times, it's almost less. It can be accuracy, but speed of convergence. If you don't scale a neural network, you can just grind and grind and grind. It takes forever. If you scale, you can get to your answer much faster. The other thing that I would do is that I would plot a histogram of the pre-scaled and the post-scaled and see if the post-scaled kind of looks somewhat normal, or a shape that is pleasing, not a scatter plot of like outliers and a kindergarten art project in the middle. So go.
I'm a bit confused as to what the scaling does. Does it increase the size of the data set at all, or?
It doesn't increase it, it just shifts it. It just transforms the data set. So imagine if you have a data set that ranges from 10 to 100, and the mean is 60. It's going to subtract the mean and then scale the standard deviation.
Do you have that figure that you sent me handy that one time? Like you have a perfect figure that you sent me that demonstrates the gradients.
Oh yeah, I'll try to find it, but I'll find it when my screen's not sharing. So yeah, groovy. Okay, so pre-processing is good, There's a small subset of models where pre-processing isn't super necessary, but I would say those models are relatively unique and rare. Within the Scikit-Learn pre-processing ecosystem, there's 4, 5, or 6 different pre-processing things you can do. We just are doing the most basic one here. Okay, so how many of you have looked at papers with clustering or unsupervised learning or something like that? I'm getting some nods, some hand waves. Okay, so we are going to cluster this data set. So here we're going to set the number of clusters to 3. We have already imported this Kmeans algorithm. So the number of clusters equals num clusters, so which is 3. The random state equals 3. You set the random state if you want it to be repeatable, if you want to have a similar answer every time. If you don't set random state, you might get slightly different answers every time. Even with setting the random state, you might get slightly different answers every time. Ooh, the joys of machine learning. But it is one way to sort of limit that. And then the initialization to auto, and then we're going to, from that K-means model, we're going to fit it, so dot fit. We're going to only use the float columns from the DF scaled data frame. So this is really all one line that I put out to 3, but I could easily write it like this. And then this, if you're not super familiar with Pandas, so in the DF underscore scale data frame, I'm making a new column called Kmeans. And from that, I'm going to dump in the Kmeans labels. And so in this, we can see, so we have 3 clusters. So we should see in this column, you should see 0, 1, and 2. But let's do. So the max is 2, the min should be 0. That'll all make sense. Now, if this is just basically a big matplotlib plot with subplots, but we're just going to press Shift Enter and then get to the good stuff. So the dots are clusters. On the left, it's flipper length, and then on the x-axis is species. So even though this is a unsupervised machine learning model, do the clusters sort of arrange with the species of penguin? Yes, getting some nods. Okay. And then if you did body mass, it also looks very similar. So there is some parts where it isn't perfect, but overall this clustering technique is separating out the species of penguin. Does anyone have any questions about clustering, when you would do clustering? What did I just Shift Enter through? Anything sort of like that? No? Good. There's a lot of different unsupervised machine learning techniques. A lot of times for my office hours, when people ask me about a problem and they have a big deep learning TensorFlow situation up, while you could do it that way, you can also, clustering is very powerful, especially if you're identifying bad data or weird data. This is one place where I would start just because it's significantly less lines of code, way easier to maintain, and other sorts of stuff like that. Not saying that deep learning isn't useful for some of those tasks, but I would definitely start here. Okay, next we're going to do some classification work. We're going to see if we can identify what island these penguins came from. Okay, so now I'm going to work through this next line of code. So like we heard in some of the talks this morning, you need a training and a testing data set. So you're going to have a data set where you give the computer a known x and y, and then you're going to give it a training data set where that is unseen data, and we're going to see how well it can do on that unseen data. Does anyone have any questions why we would have a training and testing data set? Or does everyone get that? Okay. The other thing that's also even better practice when you have a larger data set is probably a training, testing, and validation data set. The more data sets you hold away from your training data set that you can use to sort of quiz the model or make sure the model is doing what you think is doing, the better, I would say, or best practice. All right. So with Scikit-Learn, there's a module called test train split, and that will magically randomly pull apart these rows in a training and testing data set that all matches. So in our Y test, we have 3 unique values, which are the 3 different islands. Now we're going to do the machine learning. So we're going to set our support vector classifier model, which is SVC. We're going to do model.fit, xtrain, and ytrain. We're going to get some predictions from an X test. And then we can get a balanced accuracy score, an F1. There's all these sort of classification metrics. So again, this is 1, 2, 3, 4, 5. This is 7 lines of code to make a classification scheme of which island these penguins are from. Any questions, comments, thoughts? If you want to classify, I'm sure that we all don't want to classify penguin islands. What sort of problems would you like to work on for classification scheme? I think
Snowflake images.
Snowflake images. That might be one where I would probably do a little bit in Scikit-Learn land, but I probably would go to deep learning fairly fast. So one thing with things like snowflake images, it's called fine-grained, because the difference between snow and snowflake and probably other precipitation, well, they're very different to some of us. They're fairly close. A lot of the Google classification YouTube ads we see is like dog versus plane. Like, yes, a kindergartner can crush that, but those are very different. But a golden retriever versus a yellow lab, like both have 4 paws, a wet nose, nice tail. That sort of image classification difference is much harder to do. So I think you had your hand up.
I was going to say cloud types, maybe?
Yeah, cloud types for sure. Any other sort of classification if you had a research team of your own?
What about like weather pattern, like sea level pressure maps? Could you sort of cluster? Well, I guess we're classifying.
Yeah, but you can cluster that too. Yeah, I just did a clustering scheme for atmospheric rivers. Like you can say like, oh, like is this a atmospheric river type 1, type 2, type 3? Let's see what the computer thinks how many types there are. So, yeah, go.
I've classified atmospheric transport with the self-organizing maps.
Yeah.
That's essentially Kmeans clustering, but with some 2D dimensionality between the different clusters. So
Yeah.
very similar to what we just did in here.
For sure, yeah, and you can do, it's weird, self-organizing maps isn't within Scikit-Learn, but there's a couple good packages in Python that I like that I did. Yeah, exactly. So if you're interested in self-organizing maps, feel free to get in touch. I have a nice tutorial that works through some of that. Any other sort of classification work you'd want to do, it could be outside of atmospheric stuff. All right, sweet. Well, with that, we're going to do regression. So we're going to try to predict the body mass based on bill length and bill depth and flipper length. So maybe these are correlated, these are not. Again, we're going to use the same train test split in Scikit-Learn. We're going to get an X train. I just put an R at the end for this regression data set. A Y train R for this regression data set. We're going to use a K nearest neighbors algorithm, and we're going to use 3 neighbors. And then for the predictions, I'm going to do knn.fit, X and Y, and then .predict with the X test. Then we can make some plots and histograms. We're going to do the test set is what we held out. Test set is the truth. The orangish histogram is the predictions we just did. And if you wanted to kind of plot, scatter plot a test of predictions, you can also do that. If you want to calculate RMSE, explain variance score, R squared, you can do that all within the Scikit-Learn ecosystem. So this is a very high level. I know that there's a varied audience in here. The biggest thing I want to communicate is for a basic prototype, you can do machine learning 10, 15, 30 lines of code. It's not 300 lines of code. Some things that I would do for this, I would do way more EDA, plot way more data sets. I would probably hold out a validation data set as well, that kind of keep lock and key to the very end. There's other things that you could do to sort of build on this, but for an initial exploration for basic machine learning, it doesn't require a PhD. So I know that we have plenty of time. I would like, if you have questions, want to work through your own problems, have other thoughts, I'm happy to work through stuff up here on the Zoom. Anything else, this is going to be your time to bug me and John and about any sort of questions you might have, or when and why you would use machine learning, or when you shouldn't use machine learning, or any sort of anything else. But yeah, that's all the information I had. Yeah, feel free to raise your hand or come up, or I'll float around, and thanks so much. Yeah, go for it.
So for the classification versus regression, did you use the same data set for both?
Yeah, I use the same data set for both. My target variable for regression is going to be a number, and my target variable for classification is going to be an island. You can use penguin species, whatever you want to use. But you can use the same inputs, different inputs. I would say if you're really interested in this stuff, like remove some of the inputs and see how much worse it does. That's something that I do very commonly with some of my work.
Yeah, I was kind of curious. Oh, sorry, if someone else had a question.
No, go. I would say, yeah, go for it.
So with mine, I actually have been thinking about how to apply this to my master's research.
Okay.
How small do you think is too small of a data set to use? Because my data set's not very large, because I did a lot of observational data.
It depends on what you're trying to do or how many classifications you have. If it's a binary thing of like tornado versus not tornado, that's an easier problem than tornado class 1, tornado class 2, tornado class 7A. I'm not a meteorologist, I have no idea if that means anything. I'm just saying, like, the more different things you're trying to predict and the more varied or more lopsided that data set is, the harder it is. So you kind of need to be, the smaller your data set, the more of a lumper you need to be. But if you have 100,000 data points, then you could potentially get a little bit more finer tuned outputs. But if you have a truly small data set, do a big unsupervised project. Compare Kmeans to some clustering stuff, and that doesn't require, you can compare, do my labels match up with the cluster labels? And that can be an interesting kind of road to go down. If you have 100 data points, 1,000 data points.
What about 30?
Yeah, 30, I would do clustering. I would start and end there, and stats. So.
I haven't done clustering either, but I'll have to look into that.
Okay, yeah, perfect.
Why don't we do that first?
Go for it.
So, as I was saying in my talk earlier, we do a lot of teleconnection stuff.
Okay.
And it's like monthly, we got monthly numbers going back to 1950.
Yeah.
And you slam together 8 of these and you get cold or warm, wet or dry. I'm thinking a regression would be the best way to do a test or a train and test to get to a hot or cold
Yes,
based on the.
especially if it's some metric that
Yeah.
you're kind of shooting for.
Mhm.
I don't like to bin things into hot, like if you have a number from like 20 to 85 or let's do 0 to like 40 in C in Celsius. If that's your underlying data, I don't like to bin it into like hot or cold or medium, like just let it predict the number. There's pros and cons to both. It depends on how you slice it, depends on your data set. I'm not going to say like, oh, you can never bin because that's, there's no absolutes in machine learning. But yeah, I think a regression could make sense for that problem. The other sort of thing, if you have data sets back to the 1950s, one thing I won't say machine learning struggles with, but there's some climatology there.
Yes.
And so is machine learning better than generalized climatology within the error bars? It really depends on the problem. Sometimes machine learning is just another way to get to that answer. It's not better or worse, it's different. It's another tool in the toolkit, but I'm not going to say like, oh, machine learning is going to revolutionize climatology. It can for some problems, but it won't hit it out of the park for all.
Can I add an aspect to that or a coder to that?
Yeah, for sure.
So when we do this stuff, you're right, climatology, there's some truth to that. But with climate change, climatology is now meaningless for a lot of what we do. Climatology, the 1991 to 2020 climatology for the United States. So like every summer, we forecast a top 10 warmest summer on record. That's our baseline. And if it's not, then it's a cold summer because of what climate change has done. Just as an FYI, that's the world we live in now. That seasonal forecasters start at, this is going to be the 10th warmest summer ever, and you work from there. So is there a way within this regression that you can lean into the fact that you're warmer now than you used to be?
Yes, so
Okay.
I would say in general, your training and testing data, you want it to be sort of representative of your problem. So it can be hard if your training and testing data is from 1995 to 2015, and you're wondering, well, what's going to happen in 2025? There are some methods that extrapolate. There's some methods that don't. And so I would, you would want to sort of experiment with that. If you know, like, my training data set is not going to be super representative of where I want to be, you might want to lean into more like linear regression, but you heavily pre-process the data or some of those methods compared to other things that don't extrapolate well. Yeah, ask ChatGPT, or you can ask me too, but John, go for it.
We had a question. I'll do. Is it green? No, I just went off. I'll just yell.
Okay.
We had a good question from Pete from Zoom, which I answered, but Thomas, maybe you could actually do it through the Jupyter.
Yep.
And he basically says, can you map the results back to the original, not pre-processed data set? That is, show the model results, but using the original bill size, depth, etc. So, in other words, the histogram that we're looking at here,
Yeah,
it's still in the scale.
It's still in the scale because, yeah, you don't have negative 1.5 millimeter bills. I'm not a biologist, but that doesn't make sense. But
Yes, you can use, Thomas used a function, the standard scalar, in order to do the transformation. So there's a complementary method that goes with that, called inverse transform. Okay, so that's what you would then do to get back into like your units data, right? If the here was millimeters. Yeah, Thomas has got it up there for you.
so I'm just going to drop it in the chat. But yes, so one thing, also kind of did some bad machine learning. You should also kind of pre-process your data after you split. So I did kind of machine learning no-no. But you can transform it back to its original sort of millimeter range, but it won't be exact. So that's one thing where, especially with, I have a lot of experience with like decision trees and gradient boosted decision trees where I scale things, run the model, then unscale it, or I run it on a data set and I don't scale it at all. And there will be some differences in the predictions. Now, whether that's statistically significant or different enough to matter, But you know, it really depends on your model. But yes, you can get to the original sort of shape of your data as long as it's too weird, but it won't be perfect. Kia, go for it.
I guess I'm just interested more in the self-organizing map piece, since that's kind of my starting point at understanding machine learning. And since Aaron's in the room and I've done a lot of it before, like, I think it's also an accessible point for students to understand, because they can think about like classifying weather patterns that they've seen on their maps. And so I guess I was just wondering if you could point me to the goodies you were talking about.
Yes, okay, so I don't have this notebook on the Jupyter Hub, unfortunately. But here, I'm gonna just drop it in the chat. I can probably put it up there later. I just put it in the Zoom chat. So this, I borrowed the data set. Here, there's, oh yeah, I borrowed this from a friend of Unidata, from Craig Ramsayer. He's over at Virginia Tech now. He has a paper on classifying East Coast atmospheric rivers with self-organizing maps. Unfortunately, this data set only has the atmospheric river picked, so I don't have the non-atmospheric river picked, but you can, once you have that data set, you could just drop it in here. But yeah, so this, I'm just gonna run through it really quick, but Kia, I'd be happy to chat with you later. Where, yeah, for the East Coast atmospheric river data, so we load in this netcdf file. Here's what some of the timestamps look like. I think this is IVT. Again, I am not a meteorologist, so if I butcher everything meteorology related, you can see me after class. And yeah, so you can use, long and the short of it, you can use, so these are different clusters, and it has the median IVT value for each sort of time step. So you can see sort of the more energetic ones are in cluster 0, and then the less ones are in cluster 2. I think actually Kevin has expanded this work to some other GRIB files. He's done some cool contouring, and I've been meaning to bug him about it. But self-organizing map tutorial's been on the tip. It's here, but I'm open for feedback how to make it better. This is just kind of a first pass.
So my student has some pretty good examples that we could probably share with you if you want, like the two-dimensional MSLP data, outputting patterns.
That'd be great. Yeah, I'm always hungry for what people actually want, and it's tough. Like, some people are like, oh, I need a WNet TensorFlow, all the GPUs, and some people are like, oh, a self-organizing map would be great. So, you know, there's just a lot of ends of that spectrum for sure.